Okay, so I gotta step away from the camera and shield the thing. So we're talking about question number 2 in Grant Sanderson's video here, which is when you project down to the plane, what do you get?
Mm-hmm.
So why don't you draw the picture and show what we're talking about here?
So you have a sphere, and we're looking at a ring in the sphere. And this ring, we found in the previous part, had area of 2 pi times r sine theta, where theta was the angle to the ring.
That's not the area.
That's the circumference of the ring.
The circumference, right?
Theta is this angle, and r is the radius of the circle.
Okay.
So then the area of the ring is found by multiplying the circumference by the thickness, which was, because it was r times d theta. And you change r, move r slightly, and the resulting angle. That's the length right up here.
Okay. All right, that's the length along the essentially along the surface of the sphere. Okay. And so how does that expression simplify for the area of this ring?
So this is 2 pi r squared, this is all constant, times sine theta d theta.
Okay. And he said you could just integrate now if you know calculus. So what integral would you do?
So you do the integral from 0 to pi. Well, you can pull this out, so 2 pi r squared times the integral from 0 to pi of sine theta d theta. Which turns into 2 pi r squared times minus cosine of pi minus cosine, so plus cosine of 0, which is 2 pi r squared times 2, which is 4 pi r squared, like we said.
Okay, great. But now what we're going to do is just try to find the area of this projection of the shadow when you move it down to the what would we call that? To the disk at the base of the sphere, I guess.
Mm-hmm.
Okay. So why don't you let's erase this. Looks like the area up here at the top. That's our area.
Area is 2 pi r squared times sine theta d theta.
Okay.
So I'll draw a new picture. So we have our triangle. We have theta, r, and right triangle, and this is r sine theta. So to look at our ring, we can look at what the sphere is like nearby. It's like that.
Okay.
So we make a triangle, another triangle. It's kind of like this. I thought it was bigger over here. So this triangle, the hypotenuse is r times d theta. From the small change in theta, if you extend this back to here.
Okay.
This side is what we're trying to find. That's our projection width, which I'll call x, and it's another right triangle. So we can approximate this r d theta. We can extend it to approximate a tangent to the sphere at this point. So we can say that we have a right angle between this radius and the tangent. We can say we have a right angle here. And we can say we have a right angle here. So we know we have a right angle here. And this is 90 minus theta. We know these two, since these are both right triangles, we know these two sides here and here are parallel. So we know this angle or no, not that angle, it's this angle. It's theta. And then because we know this is also a right angle, we know this is 90 minus theta.
Okay.
So it's here. This is theta.
All right, nice.
So from this, we know that cosine theta is x over r d theta. So we know x is cosine theta times r d theta.
Nice. All right.
So width of our disk.
So what is the approximate area of the disk going to be when it's projected down then?
So instead of having the r d theta, you have cosine theta times r d theta.
Okay.
So it's going to be long, but we have 2 pi. I think we just had a cosine. So 2 pi r squared sine theta d theta times cosine theta.
Yeah, usually you would write the d theta last. So sine theta, cosine theta, d theta. Cool. Good job. All right. That was great work. So tomorrow we will answer the third question.
All right.
All right. Good work, hon.